Welcome everyone to the long-awaited Thevenins demonstration. This is going to be a good one because we're going to apply things that are happening real on a circuit that we can measure to what we do mathematically on the board. So as we talked about in the original circuit analysis video, is that Thevenins voltage and Thevenins resistance are measurements that we would take on a circuit. They're just from the perspective of 2 points. And so in order to know what Thevenins voltage should be and what Thevenins resistance it should be, we analyze a circuit using Ohm's law and voltage drop, like proportional voltage drop theory. So we're going to do that here with an example that we've laid out physically on our board. So Carlos is over there. He's he's here. But he's got a document camera pointed down at what's called a breadboard that has a circuit built on it. And that circuit I have made a schematic for here on the board. And so let me draw this. We have essentially a 1000 ohm resistor in series with two 470 ohm resistors that are in parallel with one another, and then returning back to this. And we are going to do our measurements that this black box are from points A and B. So we're going to be touching our voltmeter and our ohm meter to those 2 points around that resistor. So we're going to calculate RThev and VThev from that perspective. Now let's switch the camera over to the document cam, and we'll kind of point out what's happening on the circuit here. So on the circuit here, steal that pen so that I have a nice point to point at. We've got our positive terminal of the breadboard here. Each row is connected here. So it goes from the positive terminal through this 1000 ohm resistor, and then all of these are connected. Every row is connected, but down the line, it's not connected. So then I go through the two parallel 470 ohm resistors. That's connected to a wire here, which then jumps those leads to ground. So that's how that relates to this. If we switch back to the board, we can see that it's going from the positive terminal to that 1K. On the other side of that 1K is attached to two separate resistors in parallel, and those two separate resistors in parallel are attached to a wire that goes back to our ground terminal. So this is the schematic for that circuit that we've wired up there. Now, after we do some math here, we're going to figure out what our readings should be, and then we're going to check to see what we're actually getting on these. Let's keep in mind, we don't live in a perfect world. Tolerances. Wires have resistance. Our multimeter has an error range to it. So there's many reasons why we aren't going to get exactly the same number, but we should get in the ballpark. And in the ballpark should be kind of determined by what our plus and minus range is. And those all have the gold on them. So they're plus or minus 5%, I think. So if we get within plus or minus 5% of the answer, we'll have done good work. All right, so VThev. We're going to do this up here on the board. So we're back up on the board.
Yep, we're up on the board.
So VThev, what we have to do is we have to figure out what 1000, like we're essentially just figuring out what proportion of the voltage will 1000 volts or 1000 ohms eat up out of the total voltage drop. Because we know that the voltage is going to drop all the way to zero over here, right? And it's going to drop part of the way here, and it's going to drop the rest of the way here. And that's going to be proportional to what the total voltage is. We just figure out what that fraction is. So the fraction of that is 1000 divided by the total, like the total resistance. So let's just start there. We're going to write out what that's going to be.
Yep.
So it's going to be 1000 divided by 1000 plus these two in parallel. And so when we do those in parallel, we're going to make a big parentheses here. And I'm going to do this as 1 over 470 plus 1 over 470. This is the same as 1 over our total equals 1 over 470 plus 1 over 470. I just have moved the 1 over here to create the inverse function that we need.
What about our source voltage there?
Oh, sorry. It's times 9.5. We've taken a reading of this particular one. The battery is reading out at 9.5 volts. So 9.5 is the voltage that we're going to do it. Because VThev is this proportional fraction times the total voltage. That's what we're going to get from the proportion of that that's going to be eaten up by this resistor alone, the voltage drop across this resistor. Mm-hmm. So if we've got 1 over 1,000, or if we've got 1 over this plus this, we can shorten this up, right? And we can do this with fractions. If it's easy to do it with fractions, we'll do it with fractions. If we need to do it with decimals, we do it with decimals, but we don't round, because anything we round is going to be an error later on. So what we're going to do is we're going to do this, and this we can do real quickly. So that's going to be 1 over 2 over 470. And since that 1 over just means taking the inverse, 2 over 470, 1 over 2 over 470 is essentially equal to 470 divided by 2.
Just 235.
Which is 235. So if we do this, if we do the 1 over that, we can get rid of that. That equals 470 divided by 2. 470 divided by 2 equals 235. And that's 1,000, and we'll just carry this down from here. So that's 1,000 divided by 1,000 plus 235, which is, and all of these are times 9.5. 9.5. All right. So this then becomes 1,000 divided by, adding that up, 1235. And that equals, that's times 9.5. This part of it equals
0.809.
0.809. 0.809 times 9.5.
7.69.
7.69 volts. That is VThev. So now we know what we should read when we touch our voltmeter here and here. So I'm going to have Carlos switch the scene up so that you can see him actually take this measurement here. He's got his voltmeter on, volt DC.
Set to volt DC.
He's going to touch the two ends of that series resistor.
And as we can see there, it's reading 7.67 volts.
7.67 volts. That's well within 0.05.
Oh, yes.
So yeah, we're good there.
Yep.
Really close. So this is how you know what voltage you should be reading when you go and touch two things in there, right? It's not the whole 9 volts, because there's only a portion of the drop that happens here. The rest happens here. Pretty simple, right? And it's just really creating a fraction of the whole. That's how you find VThev. Now let's talk about RThev. For RThev, what we need to do is we need to find the resistance, but we need to short out the battery. So we're going to take this, break the battery out of it, and we're going to short around that. And when we do that, we see that this can really exist anywhere along that line. In fact, we could move that resistor right here like this, so it becomes visually apparent to us, because we have to keep in mind the spatial logic of these things. What matters is the connections, not whether they're lying horizontally or vertically. We see that the 1K is, for Thevenins, is in parallel with the two 470s. So our Thev is going to equal 1 over 1000 plus 1 over 470 plus 1 over 470. And we already know that that is 1 over 1000 plus 2 over 470, just combining those two together there. Right? And so right now, figuring out the lowest common denominator just isn't going to cut it. So we're going to want to get some decimal point values here. So I'm going to have Carlos calculate those out for me. 1 over 1000, we can figure out here.
0.001?
0.001, exactly. That's 1/1000th plus
0.004.
0.004. Is there a 25 or something at the end
There
of
is
that?
a 25.
Yeah, let's keep those.
Yep.
So we reduce our rounding errors. 0.00425. Okay? So that means that we are left with 1. I didn't do the 1 over here. Carrying it down here, this is 1 over
0.00525.
0.00525.
Which comes out to 190.
Comes out to 190. Ohms. So that is what our Thev equals. 190 ohms. We're ready to switch over to you, Carlos. Let's go ahead and see if we're right.
We gotta turn our system off. We gotta short the circuit out.
So we're shorting the circuit back out there.
Okay, we're switching our multimeter over to ohms. And we should be ready to take some measurements here. So we're coming down to 188.2 ohm.
188.2. Definitely within 5% of 190.
Yep.
So that's what you got. So the errors that we see there are, if we individually measured each one of these, we'd get closer, because what we're taking is we're just taking the value off of the code of that, and that could be plus or minus 5%. So that gives us a bit of an error there. And also there's a bit of an error measuring device, what quality your multimeter is. And then there's a little bit of resistance in the system from the wire.
Yep.
Just a tiny little bit. So in reality, it's never going to turn out to be exactly what it is, but it should be damn close.
Yeah.
And so when you go and do this, you can analyze the circuit and decide, okay, this is what it should read when I hit this. If it's reading something else, it means I've fried something. It means something's not working. If I fried this 470 ohm resistor here, I would get a very different voltage drop across here.
Yeah.
And so I would read that and it'd be wrong, but it would be a very different voltage drop, right? If I did that, the voltage drop there would switch, and you can see it would just be 1K in series with 470K. Our total resistance would be 1,470. And so this right here would be that. This is going to be actually a lower number. It would be 0.7 probably, I think. Or 0.7, 0.69 probably in there. And so then this number would be a lot less voltage on our drop. And that would just be because I fried that one open.
Yeah, so check your calculations, check your equipment, make sure if you're coming up with numbers and values that aren't making sense.
So just keep in mind, the simple flow of it. We need to find out what proportion of the total resistance this is and multiply that times the voltage. That's going to tell us our voltage drop. That's going to tell us what Vthev is. And then Rthev is just a matter of figuring out what's in series and what's in parallel and adding up the total resistance of that from this perspective. And it's once we jump that wire, and when we jump that wire, it changes the circuit. It changes it so that everything is in parallel in this one. Now, you could come up with a network of resistors. You can plot however many resistors you want on here. You just have to pick 2 points to measure from. And those 2 points determine what's in series and what's in parallel for Vthev, and what's in series and what's in parallel for Rthev. As long as you do the calculations right for adding up voltages, adding up resistances, you're going to be fine in the end. All right. That's what I've got for you.
Nice work. All right.
We'll see you in the lab. We'll be here to help you go through some of these problems in person. See you next time.
See ya.